can see, hopefully everyone can see the shared screen to my left. If not, let me know. And if I don't hear anything, I'll assume you can, and that you can hear me. So what I wanted to go through first, now it's 10 o'clock, was the syllabus. So everyone hopefully seeing that. I can make it bigger. Probably a good idea to go through the syllabus. So no issues for anybody right now? Okay. Definitely just interrupt if you have an issue. So here's the syllabus. It's posted on Canvas. You can read the blurb. My contact information. So we have these weekly Zoom sessions. A lot of people have asked if they're being recorded. Yes, I just started record. So that it should be recorded, and then I'll make the link to that available. I'm not sure if I have to send that out or if it just appears. We'll figure that out. So of course it hinges on everything working right, you know, of course. So, but I'm also available by individual Zoom sessions by appointment. So just shoot me an email. Hopefully you have all the issues with accessing the textbook, hopefully have been settled now with my recent announcement. I know some people had trouble getting to the ebook, but now hopefully they can. So that all was a new experience for me, interestingly. But and then you should have seen already, there's been one YouTube video posted, and I'll continue on lecture material in this live session, which will be recorded and posted, and then whatever's left probably will make it into the third or into the second video, third maybe, this unit for the chapter 12 unit. I'm making the videos as we go along, since I haven't taught this class online before. So they'll be, you know, look for things to appear one by one throughout the week of each unit. You may have noticed that I've also put on Canvas another sort of like worksheet. So I'll have little, you know, what in the past would have been handouts will appear on Canvas. And then a little later, the answer key to that will appear and so on. You may have seen the announcement on also other resources like the PALS tutoring, they call it. Not sure what part of the university that comes from, but it's not from the chem department, but it's a tutor that has had this class before. So that's a resource. And I'm in the process of making more practice problems available through the Pearson Publishing stuff, but I haven't done that yet. And there's plenty of problems to work that I have assigned in the chapters. So those should really always be number one, I would say. So in each Canvas module, you'll see like the reading and suggested practice problems. So the idea is that those get you ready best for the upcoming quiz. I guess I call it a quiz. I'll talk about that more later. So I would really strongly recommend molecular models. Often people, even in my regular organic sessions, Chem 361, even into the third quarter of that class, I will get questions from students where once I delve into the question further, what their problem was, it becomes clear that it's an issue with going from what you see in 2 dimensions on the page or on the screen and what you see in 3 dimensions when you build a model. And so that transition is, you know, if you can't make that transition easily, it can affect how you can solve a lot of problems in organic. So, however I end up deciding to do the quizzes, which is still a little bit up in the air, they will, if I can do it, they'll probably be timed, but maybe not. I'm struggling with this, and so there'll be a final answer on that soon. I had set aside Fridays for quiz day. That may have to change. I haven't decided. Some people have contacted me saying they work full time during the week, so that's the issue. So, among other things. So the grading though is pretty straightforward. The quizzes, however they end up being, are 40 points each. That after 6 of them adds up to 240 points. There's a final on finals week. So 300 points and a 90, 80, 70 scale. So any questions so far? Or any technical issues of not seeing or hearing? Okay. So here's my sort of the way I look at things, and really this relates, so that you see a web there, but you could think of that as the neurons in your brain, actually. And this is backed up by research. The more you do surrounding a certain thing, the more neurons physically are built and connected in your brain as you go along. That's how your brain works. So doing the reading in the textbook, attending and engaging in these class meetings, if you can, building the molecular models I mentioned, working lots of practice problems, that's really, really key. The other online resources that are becoming available, like the tutoring and then maybe some more practice problems. Checking out the videos and really, watching them maybe, or stopping them, taking notes, watching them more than once. So all of those contribute, hopefully you can see my pointer moving, to the central part here, success, right? But this relates to what is going on in the brain always. So like, for example, if this middle one was the name of a musician you were trying to remember, and you just can't remember the name of that musician. Say it's a blues musician. You're like, who was that? Who was that? If you know, so this occupies a certain cells in your brain, neurons. If you listen to a lot of blues and can remember the names of other blues musicians, say, oh, let's see, it's not Buddy Guy, it's not B.B. King, it's not, Kenny Wayne Shepherd, or, however, all of those are in the same area of the brain as the one you're trying to remember, because you put them there when you learn their names as blues musicians. So you start saying these names to yourself, it's not so-and-so, and then finally you're like, oh, it just comes to you, right? Like a miracle, oh, it's John Lee Hooker, famous blues musician. You got that answer because those neurons are connected like this in a web. So that works the same way for anything we want to learn. If you're trying to remember why alcohol groups are polar, that specific fact, you probably lodged that fact in if you did all these other engaged activities, there's probably a lot of other facts similar to that arranged all around it, like hydrogen bonding, very similar concept. So those will help you remember the answer to that one thing. So depth and breadth of learning is what this is all about. Engaging and lots of time outside of class. Any questions or comments on that? Thoughts? Okay, I hope it's quiet, so I hope people are hearing. Can I get 1 or 2 yeses on that?
Yes.
Thank you very much. I get a little nervous after a while. Thank you. So, okay, so basically the quiz schedule here, topics. We're just going chapter by chapter, pretty much along with the book. And again, I have to decide on the quiz format. But each quiz, you'll definitely have hours, if not longer, to do. I'll say that up front. So I wanted to get to material now. Hopefully you've watched the first video, or will very soon. So this will pick up right after that. Oh, maybe I'll say a couple things about the Canvas site. So looking at the Canvas site, right now you see the syllabus, you'll see the chapter modules. Right now there's just the reading and practice problems from the book. And then I posted this extra practice set. I think in grades, there's nothing there yet, except the first, I put it as chapter 12 quiz, 40 points, but nothing else there. And what you'll see added to this will be this, access to this Zoom session, I think, unless that just gets sent out as a separate invite, answer keys, and so forth. So just keep an eye on things in Canvas appearing one by one. The videos won't be here though, those are in YouTube. And announcements will go out time to time. You've already gotten some of those, like on accessing the textbook and everything. I have a question out to the textbook folks as far as getting the answers to the odd numbered problems, which I still have not been able to accomplish yet. So I haven't assigned those. All right, so organic chemistry. Hopefully you've seen the first video. We have the concept of carbon atoms, especially because those are the basis of most molecules of living things. So organic is living thing, molecules that come from living things, but they get studied, their structures determined, altered and synthesized. That's all part of the organic realm. Carbons form 4 bonds. So the simplest carbon compound is this compound with 4 hydrogens attached, and it has a name, methane. And the ane suffix comes from the broad category of alkanes. So alkanes, methane being the simplest alkane. These are compounds that have all single bonds. So all alkanes are carbon-based molecules that have single bonds, and no matter how many carbons you have, say you had 3 of them, they would be connected by single bonds, and you would fill in the complement of hydrogens, unless you're told otherwise, so that each carbon has 4 bonds. So some of this is already in video 1. Clearly, there's lots of possibilities as molecules get bigger, where they're not just in a linear straight chain like this. So this is a linear or straight chain, we'll call it. And I think I could probably make this, I can't make it too much bigger. Strike that. No, this is in the way. Okay. All right, so in the video I talk about isomers. So this molecule above doesn't have any isomers because you can't really switch things around to get any alternative versions of this. But as soon as you add another carbon, so I'm going to draw this out again with one more carbon added. I kind of draw them, I have a habit of drawing them in some way close to what they look like, say, if you built the model, actually. But we're gonna, well, and I talked about some of that in the video about three-dimensional ways of showing structures too. But right now we're talking about isomers. So as soon as I add another carbon, there becomes another compound with the same molecular formula. So the molecular formula of this is C4H1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C4H10. That's the molecular formula. There's another molecule with that same molecular formula that is achieved through introducing a branch. And now look at what I'm doing here. I'm abbreviating already, right? CH3, CH3, CH3. This carbon still needs one more bond, right? There's another hydrogen. So this is an isomer of the molecule on the left. It has the same molecular formula, C4H10. And so as a result, we need different names for these different molecules because they're different molecules. As it turns out, and we're going to go through more nomenclature, this is called butane. And this is called isobutane because it's an isomer of butane. So, and these are sort of what we would call, no, I'm not going to go there right now. Okay, so any questions so far on this? If in a perfect world, it would be as simple as naming all the isomers iso whatever. But the problem is that as you keep adding carbons, you can have even more isomers. And so you can't just call them all iso whatever. So at the same time right now, what I'm going to do is, because you see how long it takes to draw these out, I'm going to draw what we see above very quickly in a line structure, or what your book calls condensed structure. These are the same. And it's really, look how much more quickly I could draw that. It's really critical, as I said in the video, to become very fluent with this, where you can go from one to the other very quickly. So it's not just that you can go in this direction to get to here, you should be able to, but if you see this structure, you should be able to know where all the implied carbons and hydrogens are. And you can see them above. So when organic chemists see this, they are thinking this in their mind. And you want to get to that point too, or you're going to have to draw things all out like this every time and take a lot of time. And potentially make mistakes, to be honest, when you have to draw so much. So when we add more carbons, let's say we had a molecular formula C6H14. So you're going to have problems like this that you're faced with, and how do you approach the solution to this? You know, you could start out by reassuring yourself that this is an alkane and just draw the full linear version. A lot of people like to do that first. Excuse me. So I'm just marching along in a straight line, except it's not straight, right? I'm making it jagged. Why? Because the 3D, the real version of the molecule, it has angles like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens, 12, 13, 14. Okay, 1, 2, 3, 4, 5, 6 carbons. So in solving this problem, I'm saying to myself, 1, 2, 3, 4, 5, 6. That's one version of the molecule. You can put little dots there to say that's where the carbons are, but these are equivalent structures. To find the next isomer, practice tells me that if I just make a branch, 1, 2, 3, 4, 5, 6 carbons, that this will have the same molecular formula. And as I showed in the video, what it really is just detaching here, for example, and switching it with, say, a hydrogen, one of the 2 hydrogens that's implied at this position. Disconnect this bond, switch the 2 groups. Remember, at the end here is a methyl group. So above we called CH4 methane. This is a methyl group. And we're going to talk more about what that, the ill ending and so forth. So this is the same molecular formula, different structure, same formula, different structure. And it's important to point out that, you can't take this structure and rotate it or flex it in any way to get this structure above. You have to actually disconnect and switch bond atoms or groups of atoms. You can continue finding new isomers by branching it in different ways. So if I add another branch down here, for example, 1, 2, 3, 4, 5, 6 carbons. If you put in all the implied hydrogens, which you can do on your afterward if you want, again, this is another isomer, C6H14. So you have to continue finding all the different possibilities. Here's another one, 1, 2, 3, 4, 5, 6. Let's see, 1, 2, 3, it's a little funny. 1, 2, 3, 4, 5, 6. That's another one that's different from all these other ones. That may be the last one. I think that's the last one. So now the most common error that people have is that they will continue on and do something like this. And I'll say, I'll get out my red pen and say, oh, that's the wrong color. Okay. Let's do that. Okay, so I'll go same as above. Like that one. Why is that the same as above? Anyone know? Anyone want to chime in? Okay, so the above structure here, you can rotate around any single bond freely. So if I rotate around this single bond up here, it gets me down to here. So all this is only a rotation. No bonds had to be disconnected or groups switched to get from this one above to the one below. All you had to do was rotate. And if you had your model in hand, you would see that easily. You would just say, flip. Oh, yeah, it's just spinning. It's just spinning. So this isn't an isomer. It's if anything, I guess you would call it a rotamer if you had to call it something. It's a conformational change. Okay, so you're going to have, I think, problems like this that you just saw to answer. So clearly another way, well, maybe not clearly, another way, let me go back. Another way to identify, distinguish, however you want, these 6 isomers, or 5, excuse me, if you accurately are able to name them, they should all have different names if they're different compounds, just like butane and isobutane above had different names. So we need to get reasonably good at naming compounds. And it starts out pretty straightforward. So if you look at the linear molecules, so, well, you have methane, which is, again, so methane. So you have the meth prefix for one carbon. So we could put another column here, number of carbons. 1. Methane, because it's an alkane. If you go to, you can't really do a line structure of that. It would be a point, I guess. So you don't really, but once you get to 2 carbons, you could do CH3 connected to CH3, and that has the prefix F for 2 carbons, ethane. So you wouldn't write these like that. You would write this as methane and ethane. 3 carbons, and okay, so if you draw a line structure of ethane, it would just be that. That's ethane. And so also that. 3 carbons, 1, 2, 3. 1, 2, 3. I'll go to line structures. Prop is the prefix for 3, propane. Propane. So methane, a greenhouse gas, also a fuel. So natural gas is mostly methane. Propane, also a fuel used for heating. Propane tanks, so forth. 4, butane, like in butane lighters. Sounds like simple alkanes are fossil fuels, basically. That's correct. Butane. And that's just the linear chain butane, sometimes called N or normal butane. Normal butane. So the N stands for normal. Somewhat helpful. 5 carbons, pentane. Pent, right? It's 5. Pentane. So you would have to call this technically N-pentane if you're referring to the linear straight chain version. Hexane, 1, 2, 3, 4, 5, 6, or N-hexane. Be consistent. N-hexane. Heptane. 1, 2, 3, 4, 5, 6, 7. Hept. Octane. 1, 2, 3, 4, 5, 6, 7, 8. We're almost done. We won't go past 10. Oops. And octane. Nine is nonane. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nonane. N, nonane. And then 10, decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, how about that? Decane. And decane. So these are all the linear alkanes. The main thing here is to recognize the prefixes: 1 carbon, 2 carbons, 3 carbons, so on. meth, eth, prop, but, pent, hex. We're going to use these again. So the other thing here in naming, basic naming, is let's say we have a hexane. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Let's say we put a methyl group, which I've already introduced here. Say a methyl group there. Just a line puts a methyl group there. If you want, we can draw this out again for reassurance. Keep doing this a few times, and after a while, you won't need to. CH2, CH2, 1, 2, 3, 4, 5, 6, CH3, CH2. So there's my hexane backbone, my hexane, the longest chain. That's the important thing to remember. And then I put my methyl group there. So methyl group. So in nomenclature, we number the longest chain from one end to the other, but it's not always left to right. It's the longest chain where the substituent that's what we call whatever else is stuck on the parent chain, the longest parent chain. So this molecule we would number from this end, 1, 2, 3, 4, 5, 6. Rather than numbering it from the right side here, 1, 2, 3, 4, 5, 6, because that puts the methyl group substituent at 5 instead of 2. So number the longest chain, placing substituents, substituents, collectively, I'll say, you'll see what I mean by this, with the lowest possible numbers. Okay, so 1, 2, 3, 4, 5, 6. The base name, the parent name of this molecule is N-hexane. It's 1-methyl N-hexane. Putting dashes in between all those. So that's our first foray into nomenclature, naming of organic compounds. The goal of naming compounds, really important, is that if you have the name, there is only one structure that you can draw from that name. And vice versa. So from a structure, there should only be one specific name. Of course, it gets really complicated. And so, what we are aiming for is a way to converse at a basic level. And so you'll see that I won't, you could spend all quarter on nomenclature, literally. So goal. No ambiguity. Meaning, given a name, there's only one structure. Can be drawn from a given name. Clearly, you don't want you don't want to be guessing. Scientists definitely don't want to be guessing. So like, no one would come up to me and say, do you have any hexane? And they're thinking this molecule. It's like, well, that's not hexane. That's 1-methyl N-hexane, a completely different molecule. So that's the idea. Since we need to do this, well, and let me pause. Any questions on this so far? What we would refer to this as one of the rules of nomenclature. Start by numbering the longest chain, putting the substituents at lowest combination or possible numbers.
I have a quick question.
Excellent, yeah.
So you said what the N before the name means, but I don't think I caught what the M means.
Oh, normal.
Okay, so both the N and the M mean normal?
Oh, sorry, this is an M, not, sorry, my script writing, yeah.
Okay, thank you.
Yeah, there's no M by itself, just always N. But thanks for noticing that. So yeah, someone at some point said, well, what are we going to call the linear chain parent compound? Well, let's just call it the normal one, normal. So we need to be able to name, like we have the methyl group already defined. So it's not methane, it's methyl. When it's a substituent, often you add the YL suffix. So this methyl group is a substituent. I can indicate that that is connected to something else variably by this squiggly line. So what this means is connected to something. So in very similar way as the regular naming that we saw above, you could have an ethyl group. So an ethyl group connected to something else would be this. That's a 3. That's an ethyl group. So you're using the same prefix. You don't have to learn a new prefix, thankfully. 2 carbons is eth, 1 carbon methyl. Notice I didn't do this. If you can do that, you'll see that done, but I'm in the habit of always trying to indicate that the bond is between the 2 carbons. And this has this weird squishy feeling of like, oh, the carbon is connected where? Is it connected to 2 hydrogens? That's impossible, right? So, so in general, you want to, if you're doing the reading, if you're watching the videos, if you're working the extra problems, you'll gravitate toward writing things down in the same, more correct way that you see it done in the book, in the problems, for example, in the videos. Don't make up your own system. I can't emphasize that enough. So I've seen people, so I'm gonna digress here. I'm gonna shamelessly digress by saying, don't do this. Don't make up your own systems. And for example, some people would do this. You know, like, oh, there's a carbon here, H2, like floating off next to it. You know, I've seen all kinds of stuff. So, okay, I think I don't need to go too far into that right now. Continuing here, so an ethyl group is this. And so this squiggly bond is cutting the bond in half. So there's not a carbon on the end here. No carbon here. It just means that it's connected to something else. So here are the two carbons of the ethyl group, abbreviated. So these are the same. The next one would be a propyl group, 3 carbons. 1, 2, 3, propyl group. But then we have an isomer of the propyl group, which also has 3 carbons. Oh, how about that? So that's an isopropyl group. Again, you're going to see a lot of inconsistency in what is supposed to be consistent methods of naming. You'll see this soon. So there's 2 propyl groups, and I guess technically an N-propyl group and an isopropyl group. Sometimes you'll see this as 1 propyl. That seems less clear. Then once you get into the butanes, you get more isomers. So N-butyl, 1, 2, 3, 4 carbons, N-butyl group. Now this has other isomers like branching ones. So 1, 2, 3, let's start. 1, 2, 3, 4. 1, 2, 3, 4 carbons, isobutyl group. So far, so good. Kind of making sense. But then since there's more, the names get wackier. So this butyl group, 1, 2, 3, 4. Again, it's different, right? You'd have to disconnect and switch groups, breaking bonds and switching to get from any of these to the other one. This is called a secondary butyl group. Or sec-butyl. And the reason is because over here we have what's called a primary carbon. It's connected to only one other carbon. That's how that's defined. Your book goes into this as well in the reading. So connected to only one other carbon. We're getting a lot of terminology here, but I actually, believe it or not, I didn't want to do it. Try to limit the use of terminology because you can really go crazy with it. This carbon is secondary carbon because it's connected to 1, 2 other carbons. Two other carbons. And then, so likewise, here, we have one more isomer where there's 4 carbons. 1, 2, 3, 4 carbons. The tertiary butyl group, tertiary butyl, or tert butyl, And as you might easily see, it's logical progression, right? Primary carbon, secondary carbon, tertiary carbon. Connected to 1, 2, 3 other carbons. So, you know, it kind of makes sense, except for the iso. Really, it's the isobutyl that doesn't fit with the system, right? But that's the way it is. So these are the names, basically, of constituents. If we come back up here, we could title this whole section Names of Common Substituents. And of course, and now I have to glance at your book. Your book might show you the next series, which are a bunch of pentyl substituents, you know, with 5 carbons. But I think, you know, that falls into the category for me of like, go on and on with this stuff. In the time left, I just want to show an example of how this stuff is used for stuff. Let's see, find a good example here. I want, if I can squeeze in 2 more examples, that'd be great. Okay, so here's one. Give the name of this molecule. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to put some things on it. Like that. Okay, so find the longest parent chain. So longest chain, 1, 2, 3, 4, 5, 6, 7, 8 looks like it's going, that's what it's going to be. But look at over here, make sure, like, so 1, 2, 3, 4, 5, 6, 7. No, that's not as long, right? So you have to, sometimes the longest chain is not the most apparent one at first glance, but in this case it is. This is an octane of some sort, an N-octane. It's a substituted N-octane. 1, 2, 3, 4, 5, 6, 7, 8. Puts the substituents at the lowest combination of numbers, right? If I had numbered from right to left, it would have been 1, 2, 3, 4, 5, 6 substituted rather than 3, 4 substituted. What are the substituents? Methyl, methyl, ethyl. So we would go 4 ethyl, that's easy. And then 3 is really 2 methyls. So there's a way to say that. And then there's some redundancy here. Technically, you would call this 3,3-dimethyl and octane. And I put, really better fitting to match all the rules would be 3,3-dimethyl. I think this is correct. See, I don't even know all the rules, but 4-ethyl and octane. Here, I'll tell you why I'm not 100% sure. These, first of all, both of these are in a, by my earlier definition, there's no ambiguity. Given each of these names, you can draw only this structure and not some other structure. So I would credit both of these names. What I'm not sure of is if E comes before D, or if or M. I'm sorry. If E comes before M, you know, and you don't count the di, or if D comes before E. That's those. There is a rule for that, and that's, I don't remember if the di counts as the alphabetical part. So I'm, you know, I think that's even too ridiculous to get into those kind of details. I would accept either of these names for these molecules. And then, and so just in the minute remaining, let's do one more little thing here, and put like, let's do this. Okay, so what would this be named? 1, 2, 3, 4, 5, 6, 7. So it's a heptane. An N-heptane is the longest chain. You have a bromine at 4, an isopropyl group from above at 3. So I would call this 4-bromo. If it's a bromine, it's bromo. 3 isopropyl N-heptane. So with halogens, a halogen, you know, we name them fluoro, chloro, bromo, iodo, and we usually don't go past those. So halogens as substituents. As substituents. And the dye business, you know, you could be mono, di, tri, tetra, penta, hexa, and so on, etc. So those are a little bit different. You know, all of these are essential terms in this video. Believe it or not, I'm excluding a lot of non-essential terms, and I will continue to do so throughout. But at the beginning of the course, we have a lot of new terms. So I'm just 2 minutes over time. Any questions on this last bit? Okay. Well, I want to thank you sincerely all for coming. Hope to see you every week. Hope you can find these in-person, not in-person, live sessions useful. Of course, the great advantage is that you can ask questions as we go along. So please don't hesitate to do that. And then I'm assuming the recording's going to work and this whole thing will be posted. So look for the next video as well to finish up chapter 12 stuff. And look for announcements on how exactly I'm going to manage the quizzes. Stay engaged in all the aspects of the web of the course, and you should be doing great, I think. And otherwise, I'll sign off.
Thank you.
Thank you.
All right, thank you. Stop recording. Okay.